Have you ever wondered how a huge file, like a big photo or a document, gets squeezed down into a tiny little zip archive? Well, a huge part of the secret is this absolutely beautiful, simple algorithm that's been around since 1952, and it's still a cornerstone of how we do data compression today. So let's dive in and unpack how it all works.
So here's the big question, right? How can we take a file, shrink it down, sometimes by a ton, and then be able to bring it back to life perfectly without losing a single bit of information? That's the whole magic of what we call lossless compression, and Huffman coding is one of the most elegant ways to pull it off.
You see, the core of this whole puzzle isn't really about the data itself, but about how we choose to represent it. The secret sauce is all about finding a smarter, more efficient language to describe the exact same information.
Think about it like this. Most standard systems, like ASCII, give every single character the exact same amount of space, say 8 bits. It's simple, sure, but it's also wildly inefficient. I mean, in English, the letter E is everywhere, while Z is pretty rare. So why on earth should they take up the same amount of space? The brilliant idea here is to give the really frequent characters short codes, and the rare ones longer codes. That's the whole heart of variable length encoding.
Okay, but you might be thinking, hold on. If we have codes of all different lengths, how do we avoid it becoming a complete jumbled mess? How does the computer know where one character's code ends and the next one begins? Well, this is where a really clever rule comes into play.
The solution is something called a prefix-free code. And the rule is actually super simple. No code word can be the beginning or the prefix of any other code word. That one single constraint is what makes the whole system work. It means the second you've read a valid code, you know exactly what character it is. There's zero confusion.
Just look at this example here. In the bad code, A is 01 and B is 011. So if you're reading a stream of bits and you see 011, well, is that the letter B or is it the letter A followed by a 1? You have no idea. It's ambiguous. But in the good prefix-free code on the right, every path is unique. The moment you've finished a code word, you've found your symbol. The decoding is instant and totally clear.
So the big question is, how do we find the best possible prefix-free code for our data? The answer is just fantastic. We build something called a Huffman tree. And the process for building it is surprisingly simple and, honestly, pretty fun. Let's build one right now. The strategy we use is what's called a greedy strategy. I want you to imagine that each of our symbols, every letter, is its own tiny little tree, just sitting in a forest. The algorithm does just one thing, over and over again. It looks through the forest, finds the two smallest, least frequent trees, and merges them together to create a new, slightly bigger tree. You just keep doing that until you're left with only one giant tree.
Okay, this slide walks us through it perfectly. Let's do it. We start at the bottom with all our characters and how often they appear, their frequencies. So step 1, we find the two with the lowest frequency. Here, that's E and F. We combine them into a new parent node that has their combined frequency. Okay, step 2. We look at our list again. What are the two lowest now? Looks like C and B. So let's merge them. Step 3, rinse and repeat. Now the new node we made from E and F gets combined with D. You see the pattern here? We just keep going, always picking the two lowest frequency nodes available and merging them until everything is connected all the way up to a single root at the top.
And here is the magic. The final structure of this tree is the optimal code. It's so elegant. The most common symbols, like A in our example, naturally end up with very short paths from the root of the tree. And the really rare symbols, like E and F, they get pushed way down deep into the tree, giving them much longer paths. And to get the actual code, we just say going left is a 0 and going right is a 1. The path to the letter is its new code.
All right, so the method feels right, doesn't it? It's intuitive. But is it actually, mathematically, the best we can do? And how fast is it to run? Let's take a quick look at the proof and the performance.
In terms of performance, it's fantastic. Now, building the tree is the heaviest lift, but even that is really fast. It's what computer scientists call O of n log n time. But here's the key. You only have to build that tree once for a given file. After that's done, the actual encoding and decoding of your data is lightning fast. It's a really efficient trade-off.
So why does this simple, greedy strategy actually work? How do we know it gives us the absolute best tree every single time? Well, it all comes down to this core property. There's a mathematical proof that shows in any optimal code tree, the two rarest symbols will always be siblings, tucked away together at the deepest level.
So by merging them first, the Huffman algorithm makes a locally smart choice that's guaranteed to lead to the global best solution. It's simple, but it's provably perfect.
And I want to be clear, this is not just some cool academic exercise you learn about in class. No way. You are using Huffman coding every single day, probably without ever realizing it.
From the zip files you download, to the PNG images you see all over the web, to even being a part of the JPEG compression standard, Huffman Coding is an absolute workhorse. It's a foundational piece of the deflate algorithm, which is hands down one of the most widely used compression schemes on the entire planet.
And what's just mind-blowing is that this algorithm was invented by David Huffman way back in 1952. He was a student at MIT at the time, and the story goes that he came up with this brilliant idea for a term paper as a way to get out of taking the final exam. It's become one of the most successful and long-lasting algorithms in the history of computer science. Pretty cool, huh?
Now, it is important to know that Huffman isn't the only game in town. There are more advanced methods out there like arithmetic coding that can sometimes squeeze out a little bit more compression. But Huffman's big advantage is its sheer simplicity and its speed, which is exactly why it's still so popular and so widely used today.
So if you remember just one single thing from this entire explainer, let it be this. The entire genius of Huffman coding, the whole shebang, can be boiled down to this one simple, powerful, and beautiful idea: give common things short codes and rare things long codes.
That simple takeaway is incredibly powerful, but it naturally leads to some deeper, more interesting questions. Like, what happens when the frequencies of your symbols aren't fixed? What if your data stream is constantly changing? And what if your goal isn't just to make the file as small as possible, but to optimize for something else entirely? And that, my friends, is where things get even more interesting.